Well, it is time to start discussing about chapter 18, which is pretty much about chemical thermodynamics. And to start understanding how chemical thermodynamics works, then we need to start talking about spontaneous and non-spontaneous processes. Okay? So if you remember at the beginning of the semester, we were discussing about chemical kinetics, and every now and then from there we move into the chemical equilibrium, and now here with the thermodynamics, now we're going to understand a little more about the chemical reactions. More specifically, if we compare thermodynamics versus kinetics, okay, the kinetics part, when you are studying chemical kinetics, basically the question that you are trying to answer is how reactions happen. How do they occur? In terms of what are the steps of those reactions, how fast that reaction can go, that's the role of chemical kinetics. That's the answer that you want to answer, how the reactions happen. Okay? Now, thermodynamics, it goes a little beyond. It's not only, you are not longer interested in, well, how the reaction happens. That information is pretty much irrelevant. Okay? Chemical thermodynamics wants to answer the question of why reactions happen. Okay? And they both kept thermodynamics and chemical kinetics focuses on different aspects of the chemical reaction. Here we have an energy diagram, and this is pretty much, we are familiar with this, right? Probably not from 180, but 170. This is an energy diagram, and this is representing the energy of the reactants, and this is the energy of the products. Okay? And basically you are seeing there a difference between the energy levels of the reactants and the products, right? When you are studying chemical kinetics, you don't really care about that. I mean, there is probably an enthalpy of reaction that is basically the difference in energy between the products and the reactants, but chemical kinetics doesn't care about it. Okay, chemical kinetics would care about this. This is the activation energy. Okay, it's a difference in energy, but it's not something that you can actually measure. You know. So you can measure somehow the energy of the reactants, the energy of the products, but the energy, remember, this is transition state. Okay, there is no way to measure that, so it's pretty much calculated. So that box here is what chemical kinetics worry about. Okay, how the reaction is happening. Now, for chemical thermodynamics, you are looking just a snapshot, and let's call this initial snapshot. So you are looking just at what you have at the beginning of the reaction, and a final snapshot, what you have at the end of the reaction. Okay, so those are the building blocks in which chemical thermodynamics work. And this is chemical thermodynamics pretty much controls how and when the reactions happen. Okay, so what I mean by that is, well, we have to talk about spontaneity, right? Spontaneity is something that, for example, you have a reaction, the reaction occurs without you doing anything. Okay, so if those processes just occur, they are called spontaneous. Okay, but it's not that the process just occurs. The process is occurring, the chemical reaction for that matter, if we are interested in a chemical reaction, that will happen without intervention, without any energy input, any external energy input. The reaction just happens. Therefore, non-spontaneous processes are the opposite. So if the spontaneous occurs without any input, any intervention, then the non-spontaneous processes is not that they don't happen. But for them to happen, you have to provide something. You have to either give energy or you have to give any input, provide work or something that will push that reaction forward. Okay? So that's the difference between a spontaneous process and a non-spontaneous process. Okay? Now, spontaneity has absolutely nothing to do with speed of reaction. So this is highlighted here. It doesn't have anything to do with that. Okay? So a reaction could be fast, could be spontaneous. A reaction could be fast, could be non-spontaneous. Okay? It doesn't really matter. Okay? So how fast or how slow the reaction is will depend on the activation energy and temperature, for example. But there are other factors that will control that reaction that would make it spontaneous or not. Okay, so first thing that you have to keep in mind, you have to take that off of your mind. Okay, that a process is spontaneous, it doesn't mean absolutely anything, doesn't control the speed at what that process is actually happening. And one example that we can use here is between diamond and graphite. And keep in mind here, you have these two substances here. Are they different substances? Well, not really. Both are pure carbon. Okay? It's just that they are two different presentations, if you will, of carbon. So carbon can exist in either one of these two forms. Okay? Diamond, of course, everybody likes diamonds, right? But in terms of spontaneity, you are trying to go to a state that is lower in potential energy. Okay? So that's basically what's driving the process of spontaneity. Everything tends to go to a lower potential energy state. When you compare diamond and when you compare graphite, graphite is at a lower potential energy when compared to diamond. So diamond over time will spontaneously convert to graphite. Okay? Now, for anyone that has a diamond ring around, basically you might be worrying now, okay, I'm gonna lose my diamond sometime. Well, eventually, but this process occurs at such a slow pace that probably requires several lifetimes for that diamond to completely convert to graphite. So that ring is not going anywhere. Okay? So it's still a spontaneous process. It will happen without any intervention. Okay? It will convert back to graphite, but it happens at such a slow rate that you basically don't notice it. Now, that spontaneity also controls some processes that could be reversible. Okay, so technically, spontaneity drives the direction. If that reaction can occur in both directions, let's say forward and reverse direction, then the spontaneity can control one of them. Which means for a system that is an equilibrium, if either the reverse or the forward reaction is spontaneous, then that is a driving force for the equilibrium in such a way that basically there will not be equilibrium because the spontaneity drives the reaction to completion. Okay? So if it happens that you have a process that is spontaneous, if it's a reversible process or if it's a process that potentially can occur in both directions, then the direction that is spontaneous will drive the reaction. So for example, roasting. Here we are talking about roasting. Roasting is spontaneous. Okay, the process of roasting going from here to there is spontaneous. The other process is non-spontaneous. So basically what this means is that this reaction will be driven towards the roasting constantly. There is no equilibrium situation. The spontaneity of the reaction is driving the reaction, and we will drive it to completion. Okay? Does that mean that the reaction is irreversible? Well, irreversible in the sense of chemical equilibrium, maybe. Can you revert it? Well, somehow, yes. Remember, irreversible, spontaneous and non-spontaneous, the non-spontaneity part means in order for that process to happen, you have to provide something. You have to provide energy. You have to do some intervention on that process so that you drive it in the opposite direction. Okay? Now, for processes that are reversible, they are at equilibrium. Okay? Technically, there is no driving force for assisting an equilibrium. The system will reach equilibrium. And at that point, remember, the reactions, the forward and the reverse reaction will occur in the same direction. So you can really tell that one is spontaneous and the other not. If there is one that is spontaneous, then that will drive the reaction to completion. There will be either the forward or the reverse direction. It will, the spontaneity of the reaction will drive the reaction to completion. Okay? Now, for those reactions that could happen in both directions, remember, if one direction is spontaneous, the other must be non-spontaneous. Okay, it's the opposite. If it cannot be, if it was spontaneous in both directions, you have an equilibrium system, technically. Okay, if one direction is spontaneous and the other is not, the reaction will be driven to completion. That's basically the concept of spontaneity here when we apply this to chemical reactions. Now, where does that spontaneity come from? Okay, these spontaneous processes, remember, the process will be spontaneous if the potential energy of the reactants, let's apply this directly to chemical reactions, because after all, this is chemistry, correct? So if the reactants have higher energy than the products, technically you can see that as a process that is releasing energy, your system, the chemical reaction is the system, your system is going from a higher potential energy to a lower potential energy, and you can see that in terms of a driving force for the reaction. Now, the thing that we are more familiar with at this point is the enthalpy of a reaction, and the enthalpy of the reaction basically is the heat associated with a reaction. So if we see it from that point of view, and remember, we can write this very quickly, right? So if we have reactants here and we have products here, okay, this difference here is the enthalpy of the reaction, and because the reactants are sitting at a higher energy level than the products, then this enthalpy is negative. And when that happens, you have an exothermic process. Okay? The other way around, if your reactants are sitting at a lower energy level than the products, then the difference here is still the enthalpy of the reaction, but because the products are at a higher energy level, then this process is, or this enthalpy is positive, and that is an endothermic process. So you can start thinking about processes that are exothermic as spontaneous and processes that are endothermic as non-spontaneous. But that is just a fraction of the story. Okay? There is no guarantee for a process that is exothermic to be spontaneous, and there is no guarantee for a process that is endothermic to be non-spontaneous. Okay? You can actually have both situations. You can have an exothermic process that is spontaneous, pretty much the same as a process that is exothermic, and still be non-spontaneous. Okay? So at this point, if we are talking in terms of exothermic and endothermic, we are talking about the enthalpy of the reaction. And the enthalpy of the reaction will be one factor that controls spontaneity of a reaction, but it's not the only one. Okay? There are two factors here to consider. One is enthalpy. Okay? The enthalpy change is one of the factors that will control spontaneity of a reaction, but the other one is the entropy of the reaction. Okay, and depending on the relative magnitudes of these two terms and the sign of those terms, then you can have every possibility. You can have exothermic processes that are non-spontaneous, you can have endothermic processes that are perfectly spontaneous. And we will discuss that more in detail later. So just keep in mind